Okay, good afternoon, everyone. Welcome again to this seminar. This week we will host a researcher from a different department. So this will be a nice opportunity for us to see how computer vision, machine learning, and optimization methods are used in different disciplines. I think these can be really informative for us. We have Dr. Gursel Dino with us this week. Dr. Gursel Dino has obtained a master's degree from our university, Middle East Technical University, from Department of Architecture. She pursued her studies afterwards in computational design at Carnegie Mellon University and Technische Universiteit Delft in Netherlands. I hope I pronounced that correctly. She has led and participated in research projects in both the USA and Europe on the development of computational tools and methods for building performance assessment, sustainable building design, parametric design systems, climate change adaptation, and building energy efficiency. She's currently working as a faculty member at the Department of Architecture, where she acts as an advisor of graduate studies and teaches in computational design and analysis methods for high-performance buildings. So this will be a very interesting talk for us. And thank you for being with us. And the screen is yours.
Thank you very much for the introduction. It's a great pleasure to be here and giving this talk to you. So my research is strongly motivated by an urgent need for smarter computational systems in architecture and the built environment due to several pressing issues. The first one being that the built environment is a high priority area for climate change. CO2 emissions need to be reduced by 77% in the building sector by 2050. And in return, the built environment is in need of adaptation to the negative effects of climate change. Also, the complexity of architectural systems from the level of building components to cities is increasing, and this complexity needs to be dealt with. Large volumes of data is collected on buildings and cities, which can give insight into the performance and behavior of building systems and support these data sets can support design and decision making if managed correctly. So to deal with these challenges, we need intelligent computational systems in architecture. Today, I will show you some research work that I have been carrying out at the Department of Architecture in collaboration with METU and Multimedia Informatics Department, and also involved are several other departments, including civil engineering, computer science, and electrical and electronics departments. Okay, so these projects that I will be talking on are, first of all, about how we collect, generate, process, and reason on visual data in existing buildings. And as an example, I will introduce our project CISERGE that we carried out under the roof of METU and in collaboration with Harriet-Watt University. Here, I'm going to show you two separate projects on 3D reconstruction and object detection. The second theme that I would like to address is the ways in which visual acts of design generation, and design elements can be augmented. And for this, I will be introducing the Hollow Out project that we completed in collaboration with Multimedia Informatics, and also METU HBIM, which was funded by the Getty Foundation in the USA, and some faculty members at Civil Engineering Department was also involved in analysis activities. So CISERGE it was supported by an institutional links grant by British Council and TÜBİTAK, and we very recently wrapped the project up. And here the main premise is that building energy simulation tools are critical for the improvement of energy efficiency and occupant comfort of existing buildings. But the use of simulations is rather limited because manual energy modeling is laborious, first of all, and also very much error prone. Okay. As a case study in this project, we look no further than our very own building, the Faculty of Architecture. You can see several images. The black and white is from probably 1960s, and more recent images, and the digital model can be seen next to it. The very first part of this project is dedicated to image-based reconstruction of building energy models. So here we develop a 3D construction pipeline from visible and thermal images in a room. To the right, you can see the devices, the hardware that we used, a FLIR E60 and Nikon D90. And the developed pipeline generates different models, starting from point clouds to planar surface models, and finally building energy models. And for the latter two, we developed two different methods that can estimate planes from a 3D point cloud. And also we also estimate the wall thermal transmittance using IR imaging. The pipeline consists of 5 distinct steps. The very first one is the calibration of the imaging system. The first 2 sub-steps are visible band calibration and thermal calibration. Here we manufactured a checkboard calibration object, and we calculated the intrinsic and extrinsic parameters for both of these cameras. Following came the 3D point cloud generation phase. Here we use structure from motion using a set of images captured from a room, captured from different positions within the room. And these images also are containing overlapping views from the room. So to be able to find matching pixels across different views or the key points, we use the SIFT method, scale invariant feature transform method. And after identifying these useful key points and representing them as feature vectors, the key points that correspond to the same 3D points should be found. And we compare the feature vectors across different views and identify the closest feature vectors as matching. A final post-processing step is to remove geometrically incorrect matches using AC ransack, which is an existing method. And once the 3D point cloud model is generated, we need to also correct the rotation and scale of this point cloud, because it is initially an arbitrary positioning in 3D space. So for this, we use user interaction. 3 points from the captured visual band images should be selected. And we also need to locate these exact points in the room, the actual coordinates. And then we use similarity transformations to calculate the transformation between the initial model and the transformed model with scale and orientation. 3D model generation is probably the most important step, or the first important step that leads to way to useful models that we can use in architecture. For this, we will generate a 3D surface model of a room. So 2 different methods are developed in this case: baseline plane estimation, or BPE. And here the user selects a 4-corner polygon on each wall. And the 3D points that are bounded by this rectangle are found in the 3D point cloud, and a plane is fitted to each wall. And for this, we perform several steps. We use RANSAC for 3D plane estimation, and plane fitting using a least square error plane fitting algorithm. And based on the results, we felt the need to improve upon this initial method. And a second method named robust 3D structure estimation with geometric constraints, or RSEC, was developed. And this is an improvement over the first method in that we impose a perpendicularity constraint between walls during plane estimation, and the required angles of the planes are added to the cost function, additionally added to the cost function that is used during the first method. The next step is the fusion with thermal data. So as I mentioned, different photos were captured using Nikon and FLIR. And here, all 3D points are assigned thermal values, the temperature, surface temperature values from the thermal images. And here, the intrinsic parameters of the visible band and thermal cameras and the relative 3D rotation and 3D translation between them are used. Each 3D point of the point cloud is projected onto the thermal images planes. And if the depth and projected coordinates are within the images coordinates, they're accepted as point correspondences. And the RGB color representing the temperatures is assigned to the 3D points. We also calculate thermal transmittance, which is a very important feature of building energy models, because based on this U value, we can calculate the heat transmitted through these surfaces between two different between two different environments. Here we use an existing infrared thermography method. And this method assumes that the heat transferred to the IR thermal camera sensor is the sum of heat dissipated by the element for radiation and convection. And following, we solve this shown equation also using the indoor and outdoor temperatures, as well as the reflected temperature from the wall. When we look at the results, first, our pipeline was tested in a classroom in our faculty building. It's a rather small classroom, and we use different input data set conditions. So we have 8 image data sets with ranging number of images from 140 photos to 35 photos. And the image resolutions were different. So high resolution and low resolution data sets were used, resulting in 8 different data sets. And we calculate errors related to the total volume of the room, cumulative Euclidean distances between surface vertices, and the cumulative angle differences between surface normal vectors of the walls. When we look at the results first about the point cloud generation, there is a decreasing trend in the time cost and point cloud density with decreasing data sets, and this was quite predictable. And data set size, therefore, was the most significant parameters on model accuracy. And when we look at the metrics that I just mentioned, in all metrics, the magnitude of error consistently increases from high to low number of images. And this was also somewhat predictable. Also, RSEC outperforms the second method, the improved method outperforms the initial method in all cases, except for these 2 cases. I'm not sure whether you can see my mouse. In which the number of images is high. But in the end, the 0.75 square meter volume errors in BP and 1.43 square meter volume error in RSEC are quite satisfactory for us. Some future directions as a result of what we did were, first of all, the need for automated detection of objects or building materials. For example, from the images, we can extract the knowledge regarding building components. It can identify, for example, a door with wood material. And for this, there are existing algorithms or libraries, including YOLO or RetinaNet. And this will significantly reduce manual user interaction. Also, combining together 3D models of single rooms is necessary for modeling whole buildings. For this, simultaneous localization and mapping, or SLAM techniques, can be used in the future. The second part of the CISAR project was vision-based estimation of the number of occupants using video cameras. So initially, we could model a room using the boundaries and also the windows and doors. Now we are looking at the ways in which we can count the number of people. The occupancy information is important for building energy use, because people act as thermal loads, internal thermal loads, and also they impose comfort constraints to decision making. So here we develop a vision-based method that utilizes deep learning architectures for the estimation of the number of people in a room. And we particularly look at large crowded indoor environments using multiple cameras. So this is our experimental setup, a classroom at our faculty building that we use as a design studio. This means that students use this room not only during the day, but also at night, and very typically during the weekend. The classes are quite crowded and sometimes can reach up to 150 students, and this corresponds to 2 square meters per person, which is quite packed. And you can also see all kinds of furniture and models around, so there's a lot of clutter and obstructions. And this is pretty much how a typical class looks like during our studio hours, and this is a challenge that needs to be addressed for us. And also here you can see me, and this is my very own "Where is Waldo" moment amongst the crowd. Okay, so we use 6 IP cameras within this room. 3 of them looking at the door, and 3 of them are looking at the studio, at the room. So we took continuous recordings using these IP cameras. The recordings were encrypted and immediately pushed to Amazon Cloud via secure connections. The cameras also turn on the infrared LEDs. This means that recordings can continue without any interruption under all lighting conditions. The proposed method uses 3 different, let me say, algorithms. The first one is head detection to count the number of people. Here's YOLO 3 is used. Initially, we started out with V2, but within a year or so, it was already, V3 was already out, and at the moment, I think it's at 5. So it's progressing very fast, much ahead of us, but V3 is where we left off. So for background elimination, to eliminate false alarm, MOG2 was used, and for object detection, object tracking was to benefit from the temporal continuity among object pairs in successive frames. We use CSR-DCF, and 3 different counting methods were used, or 3 different approaches for counting are considered. The first one is average counting method, which estimates the number of people directly from the snapshot of the room. Entrance counting method estimates it from the entrance of the room, from the door, by incrementally counting the people entering or exiting. So there's a continuous counter. And the combined counting method merges these through methods in that it switches from one method to another as the environmental conditions allow. The details of these methods are very well documented, and you can see these in this conference paper that we published 2 years ago. A more recent one is coming up in the future, but for the time being, I think you can use this this paper for further reference. When we look at the results, we first needed to establish a ground truth data set for benchmarking. And here we generated three data sets. The first one is in situ measurements. This is established by someone counting manually inside the classroom. The second one is involves someone counting from the video recordings on the screen. And the third one, the average measurement, is the grand mean that summarizes the two ground truth measurements. So we take both of these data sets have their limitations. They somehow overestimate or underestimate the actual values. So we use this black. We use an average data set that approximates these two. Okay, and looking at the three different methods developed, you can see ACM, ECM, and CCM. You can see that the method starts at 8:30 with ECM, and ECM and CCM are completely overlapping until there is a high number of people exiting the studio, and this introduces a lot of challenges for obstructions. So it immediately switches to the average counting method, switches to the studio cameras, because there is a lower number of students. In that case, it relies on on the other method. So you can see here the switch from ACM, switch to ACM, and switch to ECM as time progresses. So during this 10-hour measurement, ECM was used 80% of the time, while ACM was used 20% of the time. And the switch is based on the activation conditions. So when we compare the average ground truth values with the combined methods generated by our pipeline, you can see that there is a great deal of overlap between these two. So a linear regression analysis was carried out, and CCM as a predictor is significant, and it could explain 97% of the total variance, which was quite successful. When we look at the mean predicted value and mean average error, we see that, again, MPE of CCM is lowest for all ground truth measurements. And this indicates that the combined counting method that we developed has the highest prediction accuracy. ECM has the highest error, the one tracking the doors, and it reaches up to 30% mean percentage errors. But ACM, those cameras looking at the camera, can predict VREC with up to 15% error. So this means that ACM can still be used with some degree of confidence if no such combined method is available. And some future directions based on these results is that the head detection algorithm can be replaced with more recent, higher performing alternatives in time. ACM also can be provided with temporal characteristics, but also this should consider the high computational costs involved with such approaches. And also video analytics can be used to detect other temporal data, temporal data initiated by occupant interaction with the building components, for example, lighting on and off, windows on and off. And within the scope of CISAR, we also worked extensively on such concepts, which I won't be presenting today. Okay, the second class of applications, computational approaches, was the involvement of visual data in design generation and in design analysis. And this project, named Immersive Design Environments for Performative Architectural Design, a Beam-based approach, was a collaboration between multimedia informatics and Department of Architecture, and it was supported by two METU grants, two BAP grants of Dr. Sürer and myself, and you can see our students here as well. So here we developed a VR-based design tool supporting performance-based architectural design. And here we integrated 3 different tools that are used for modeling, which is Autodesk Revit, for daylighting illumination analysis, for simulating the daylighting in a room using Autodesk Insight, and the Unity game engine for tool development, for visualization, and for interaction. We also experimented with HTC Vive and Microsoft HoloLens. And this tool was customized for both of these gadgets. So here is the workflow that starts with the generation of an initial model, and the data and models are transferred to Unity, wherein design exploration, design development is made, and there is a back and forth data flow between these two, let me say, tools. And the developed tool, HoloArch, has several features, including the visualization of the geometry. And this not only includes the geometry, but also all the data associated with building elements. It allows editing and changing of the existing model. Navigation within the model is also possible. You can see that a one-to-one scale and literally walking in the building is possible, but we can look at the building from all perspectives in different scales. And we can also follow design actions, and we can refurbish or furbish the space. We organized 2 workshops in the development of the HoloArch tool to gather end user experiences and requirements. The first one was in University of Lisbon Department of Architecture, and you can see our colleagues trying out HoloLens and pinching the air to interact with the building elements. This was in 2018. And the second one was organized almost a year after that, if I remember. No, sorry, this was 6 months after that. And this was at the Department of Architecture. And you can see our own students here trying out the tool. And based on the users' requirements gathered during these workshops, we improved the tool even further. What was very interesting for us was that many of the students preferred VR over HoloLens. When I first started, I thought that HoloLens is quite revolutionary, and I still have that idea, but the students preferred VR in that it minimizes the presence in the physical world, and it completely immerses the users. within that virtual world. I think that's the main reason most of the students preferred VR over HoloLens. The case study building, we gave the students a case study building, which was an existing building. As you can see, this is a digital model that our researchers developed. And also daylighting analysis were performed here. And as a result of 4 user studies and in-depth interviews and the data, qualitative data gathered there, we could identify several points. And these concepts gave us a better insight into the ways in which VR technologies could be appropriated by the designers, including the influence on designers' workflow, performative design, augmented perception, user interaction during design. And as a result, the future directions involve further studies for user gestures in model interaction and an improved integration between various involved tools regarding analysis, simulation, and interaction. So this process, again, is very well documented. And if you're interested to see more into this project, you can follow this link. Sorry, there is no link, but you can find this in this publication. Okay, the last project that I want to talk about was a part of the Research and Conservation Planning for METU Faculty of Architecture Building Complex project funded by the Getty Foundation. Here we developed a planning document for our faculty building in collaboration with departments of architecture and civil engineering. But in this talk, I specifically would like to focus on a model, a heritage building information model that was developed during the project and how it was used for various activities in heritage planning and analysis. So HBIM is a 3D digital representation of the physical, functional, and semantic characteristics of an existing building, and it can be used for a variety of different reasons, starting from the generation of technical drawings to animation to analysis to clash detection, scheduling, or information management. To develop the heritage BIM for our project, we use laser scanning. First, we use a handheld low precision scanner for the whole building. And in a second session, we use a high precision stationary scanners, and you can see them side by side and the level of precision that each one gave rise to. And using the point cloud, a detailed heritage BIM model was developed, and this time it was manually developed. It was a long process, but you can see the different representations ranging from the actual photo to the point cloud in the second image. And here we come to the heritage BIM, different views of the model, the hidden line. This is a rendering, not an actual photo, but a render, a photorealistic render. A web-based interactive tool was developed, and we could visualize HBIM data. Okay, some more realistic visualizations. I find these quite impressive in that they quite resemble the actual building, and sometimes even better, it looks very clean and very tidy. Using this heritage BIM model, we can interactively visualize the building. So here you can see that there are some marker objects that we embedded in our model. And by clicking on these, markers, you can go to the data either gathered or generated using analysis tools. To give an example, here are two of the materials that were analyzed in the laboratory, central laboratory at METU by Çağla Meral Akgül, and the detailed analysis results can be found here. And based on the model, our team also performed environmental assessment of energy, daylighting, and some CFD simulations. So this heritage BIM model facilitated the visualization, communication, interaction, and analysis activities throughout the whole project, duration of the project. And still it is it's a model, an active model. I will request you to use your cell phones. Just take a picture using your camera of any of the QR codes and follow the link. You just need to open it in your web browser, and it will say, please tap the screen and enable device orientation. And if you do so, you will see the panoramic view of certain locations in our building, a total of 9 different locations from which you can view the environment from one single view. Okay, I think I will stop here. I will leave the slide on if you want to look deeper into our building. And I will be happy to answer the questions if there are any.
Thank you, Ipek Hocam. That was really informative, interesting for us. It's a different domain, different problems, different challenges. That was really nice. Any questions from the audience? Maybe in the meantime, I can talk about the first part. So in the first part, in the CSAR project, I was really amazed by the applications that we can have for computer vision and machine learning in this domain. Even for CSAR, just trying to count the number of people, it was really challenging because you have hundreds of people. So if you have just a few people, maybe the problem is very well solved. But when you have hundreds of people in the room, some of them are sitting, some of them are standing, there are occlusion problems, and that was really interesting. And added to that, we need to be able to understand and classify the activities of people. So some of them are sitting, some of them are working, walking, etc. And for energy analysis, those were necessary, right? And they were really, really interesting and challenging problems where computer vision can definitely contribute. Are these methods, so analyzing energy usage or performance of existing buildings, used by designers or decision makers in any way in Turkey or in abroad?
Do you mean the tools that are developed during research projects or the existing off-the-shelf tools?
Either of them. So are they widely used, or are they just mainly in academia?
I'm afraid not as much as they are supposed to be used, because there's a high level of expertise required to use them, and this expertise is typically multidisciplinary. And so there are some existing tools, but the learning curve is quite steep, and there has to be a demand from the owner's side to maintain or to for the buildings to perform better. And unless there is such a demand, I'm afraid there is very little interest in the application of tools from the designers or building operators side. Nevertheless, some larger companies, engineering and architecture companies, that design large-scale buildings that have a high risk involved in this project, they have to use them. And these are most typically used by such companies, interdisciplinary companies. The research work, similar to ours, can still deliver different tools, but they are, I'm afraid, not very usable at the moment, because you need to still pull together, you need to polish the interface for the end users to be used them effectively. And there is a level of frustration that is a result of buggy codes and not so successful interface design. And this is a very big barrier against the use of these very novel tools. Of course, our best hope is that software companies can discover the tools that we develop, and they make them as part of their own their own initiatives, their own models or software tools. But this still happens sometimes. There are some cases in which even master's projects were picked up by software companies, and they were developed into tools that we are at the moment using very widely, but this is rather seldom, I'm afraid.
Thank you. Any other question? Comment? Okay. How about scaling this to streets or cities? You know, there are issues relevant at that scale as well. So I know that you are working along these lines, so maybe you can briefly talk about them.
Of course. So far we have focused on individual rooms or individual buildings and how they could be improved in performance, but a more realistic view involves improvement on a neighborhood or city scale. So I imagine a scenario in which our mayor picks up a neighborhood and starts an initiative in which the whole neighborhood is improved. And in this case, we are in need of models, very large, gigantic models that contain large amounts of data and very long hours of simulation and very long hours of computation, which is not realistic. So in a separate project that we are starting very soon together with Sinan Hoca and Çağla Hoca, and also with ITE, another faculty member from ITE, we will be developing urban scale building energy models, and we will be using machine learning for fast prediction of building performance and fast prediction of different scenarios, improving building performance. So this is an upcoming project that we hope to start within the next couple of weeks or months. And I will be very happy to report on its progress in the future, maybe in a year or two.
Yeah, that would be nice. Okay, if there are no other questions, then...
Can I ask a simple question?
Yeah, sure.
Hi, this is Aisha Good. So I'm doing my PhD in urban energy modeling related tools. And I was really curious about your work in urban modeling. And I know that I follow your project up in ResearchGate, and I've seen that you got a granted by TÜBİTAK, if I'm right, for the urban modeling. And this is a common concern in urban modeling, like area or industry, that there's like this privacy concern that you can't really have access to data I was wondering how you will be managing that. Like, will you, like, for example, I have developed like mission, like DNN tool that created like a bunch of models, but it's not really realistic in terms of like neighborhood, because we just define like some parameters and run the model, but we don't really have access to real consumptions or real construction data. So I was wondering if your project will be developing any kind of things related that privacy concern or not.
Privacy is, yes, you're right. It's one of the challenges ahead of us to reach data on the level of thermal zones. And starting from these thermal zones, there will be a bunch of critical data points, such as the number of occupants, the way in which they interact with building components, appliances, equipments, what are their age, and what are the activities that they're involved in, and also their consumption data, heating, cooling, or heating and electricity. Let me say that we will have to reach. The first class, the ones regarding occupants, can still be approximated. They can still be, let me say, vaguely approximated by means of statistics. So, so far we could, and it's tweak data is available, publicly available, but so we were actually planning to do interviews, one-to-one interviews, and gather data with questionnaires with participants. Of course, due to the pandemics, this is something that we won't be, we are not very much willing to do. But I think we will see how that plays out in the future, whether we will be able to reach low-level data starting from the zone level, or whether we will be able to approximate based on large level statistics. A recent work that I recently published with a student of mine at CIMAUT 2020 addresses this need and tries to come up with different layouts for different residential units and assigns different family typologies to these units. But of course, these don't rely on gathered data. These are just approximations. These are just some heuristics that we had to develop.
I see. Thank you so much.
Thank you very much.
Okay, if there are no other questions, then maybe we can stop recording and continue a little bit more in Turkish in a more informal fashion. Otherwise, we can stop recording. And thank you again, Ipek Hocam.